All right, we are back. So I was chatting with one of the breakout rooms. They weren't quite sure where to start. And I said, you know, a good starting place is just to draw your axes and make a line that represents the potential energy of your reactants. It doesn't matter where that line is. And then write down, what are your reactants? 6 silver, 1 mole of iron 3 oxide. And then your next step is going to always be to go from your reactants up to the elemental form. And you have to make sure you're balancing along the way. So we talked first about iron being a solid metal. There's 2 irons, so I need a 2 as a coefficient. Oxygen turns into a gas in its most stable state, it's O2. I need a fraction. If anytime I need an odd number of oxygens, I'm gonna need a fraction. And if I want 3, 3 is gonna be in my numerator and 2 will always be in the denominator so that the 2's cancel. So 3/2 of O2 gives me 3 oxygens. I had 6 silver already in its elemental form, so I just write it up here. How do I know how much energy it takes to go from the reactants to the elemental forms? How did you guys think about that?
Is it the opposite of the like 824 to like put it together?
Yes, so one thing you have to notice is that the 824 is if you were going to be elements to product going down. So Zach's noticing it's the opposite. It's going to be a positive. But there's one more thing I have to do, because that's kilojoules per 1 mole. How many moles of iron oxide am I making?
One.
Just 1, so that one's kind of nice. So moles cancel, and I know it takes, I have to put in 824 kilojoules to go up to elemental form. How much energy is going to come out when we make 3 moles of silver oxide and 2 moles of iron?
93.
90 what?
Is it 93?
90.
Negative 93?
Yeah. So what Zach did is he said there's 3 moles, right, up here, of silver oxide. And for every 1 mole, negative 31 kilojoules is released. So 3 times 31 is negative 93. So 824, that was a pretty big, so I'm gonna make my reactants way up here. And my products. So my products are 3 Ag2O solid plus 2 Fe solid. I'm almost done. The point of this energy diagram is to help you find delta H of the reaction. So to get from here, from reactants to products, going up. So this is another endothermic reaction. What do I have to do? How do I find this?
The delta H formation reactants plus the products.
Yeah. So I got to sum together like I already did. The delta H of formation accounting for their moles. So that was plus 824 kilojoules. And then sum the heat of formations for the products. We did that, accounting for their moles, negative 93. So overall, the delta H of this reaction is a positive 731 kilojoules. So it was very endothermic and not favorable.
Can you circle the addition between like the two sigmas to like emphasize that it's not like subtracting?
Like this?
Yeah, because I thought it was like subtraction at first.
In your book, sometimes people will write, because you always are making the down arrow negative, sometimes you'll see it written like this. The heat of formation of the products minus the heat of formation of the reactants. And that's only because the reactants, they're always going to give it to you as negative, but you have to flip the sign. So if you do this version, then you would just take the numbers as given, and the equation flips the sign for you. If you draw the energy diagram, this equation is better because you've already done the sign flipping.
Yeah, that makes sense.
Okay, great. And again, your book does a pretty decent job with this. So if you go to those pages I mentioned earlier in the lecture, then that might be a way to reinforce.
So you're saying as long as you flip the signs according to which way the arrow is pointed, then you can add the two together instead of subtracting them, right?
Yeah. So here, if you already flip the signs according to the arrows, then you add. Or you just take directly from the chart. And in most cases, they'll both be negative. So you'll have a negative here, which is what you see. And then the negative will make this positive, which is what you end up seeing. So I would say choose one method that you like and stick with it. But for our class, you need to be able to draw an energy diagram to represent a reaction, and you need to be able to calculate the heat of reaction this way or this way. Is this making sense for people? I have one more problem I want to show you before we end. Okay, one last one, and I'm just going to talk through this because it's kind of new. It's an application. Okay, when you come back from spring break, I'm going to send you kind of information regarding a lab called the Hess's Law Lab, and in it you do something called calorimetry. A calorimeter is basically just an insulated system that's preventing heat from getting transferred outside of it. So if you were, let's say you were worked in a research lab or an industry and it was your job to design a hot pack, then you would need to know how much of each reactant to put in order to achieve a desired temperature change. So let's say this is the reaction that you're working with. Silver nitrate in an aqueous solution reacts with hydrochloric acid to make silver chloride and nitric acid. And when you do this mixing, the delta H of this reaction is negative 63.5. So are we talking about an endo or exothermic reaction?
Exothermic.
exo, negative sign, exothermic. So when you mix this, is the solution gonna feel hot or is it gonna feel cold?
Hot?
Hot, yes. So that hence the hot pack. When you mix these two and they react, then changes in bonding relate to changes in potential energy, and that's why you have an exchange of heat. So let's say you mix 52.7 milliliters of 1.00 molar silver nitrate with 48.9 milliliters of 0.110 molar hydrochloric acid. And the two solutions are both at the same temperature to start. That's T initial, 22.60 degrees Celsius. How would you use the enthalpy of the reaction below? And assuming the combined solution, oh, so this is telling you the mass, I changed it. The mass should have 111.8 grams of the solution. So use this, use the mass of the solution, and assume that the solution in the end has a heat capacity similar to water, 4.18 joules per gram Celsius, to find what is the final temperature of the solution gonna be after this many moles of reactants react. So this is a kind of a complicated problem. Anytime you get a problem where you're doing some kind of reaction, you better define the system and the surroundings. And whatever lecture, I think it was lecture 18, maybe we talked about this, the system tends to be the chemical reaction. So this reaction is our system. This is state 1. And this is state 2. So the system is, you know, silver, nitrogen, oxygen atoms, hydrogen atoms, chlorine atoms arranged in particular bonding models. And then there's a new arrangement in the products. The surroundings is going to be the solution, because the solution is sitting in this insulated container called a calorimeter. So we're assuming there's no heat lost to the air or even to the calorimeter itself right now. So how does conservation of energy come into play here? I need to start by writing my Q equations. And what does Q stand for? Think back to lecture 17. Q is heat. So remember, whenever we're talking about energy conserved, we put a negative if something is losing heat, like if the system is losing heat, and a positive if heat is gained by the surroundings, because heat can't be created or destroyed, just like energy can't be created or destroyed. It has to be transferred. So how do I set up my Q equations here? I'm gonna have heat of the reaction and heat of the solution. What is losing heat and what is gaining heat is a question you have to ask yourself. And since we said that the reaction's exothermic, what should the sign be here? Positive or negative?
Negative?
Negative. Exothermic. So heat's being lost by the system. This is how much heat is lost per 1 mole of silver nitrate and 1 mole of hydrochloric acid that react. So if you know that this is how much heat is lost per mole, you better start by figuring out how many moles, that's N, of, let's just say, silver chloride. You have to pick one of the products. How many moles of product is going to be made? And then you can multiply that by the heat of reaction. This will tell you the total heat exchanged by the reaction if you figured out how many moles of product that you make. All of the heat that's going to be lost from the reaction is going to go into raising the temperature of the resulting solution. So if I'm raising the temperature, I'm going to go back to my formulas. Heat transferred by a chemical reaction, we've already used that. It's the number of moles that you're producing times the delta H. Heat transfer that results in changes in temperature, now I have to use my MCAT, MC delta T. Okay. So first I'm going to figure out my limiting reactant. I'm going to leave myself room for work and I'm going to find it down here. So I can use the volumes and the molarities of the reactants and figure out which one is going to make more silver chloride and which one's going to limit silver chloride. So basically 52.7 milliliters, let me get that into liters, of silver nitrate. And that silver nitrate is 0.1 molar. So that would tell me how many moles of silver nitrate I started with, and I just want to figure out from there how many moles of silver chloride I'm going to produce. So I'll look to my mole ratio and it's 1 to 1. So if you do that, 0.0052, let's just say 7 moles of AgCl. And I have 1, 2, 3 significant figures. I'm not going to do the work, but if you figured out how many moles of silver chloride based on your starting hydrochloric acid, then you would see 0.005379 moles of AgCl. That's for HCl. So this guy is your limiting reactant. So it's this number of moles that you would plug into moles of silver chloride here. Zero 0.00527 moles of AgCl. React. And we know from the equation that there's negative 63.5 kilojoules per 1 mole. And notice, this is a common mistake. This whole quantity has to be made negative because the solution is, or the reaction is exothermic. So some people think that you're accounting for the negative here, but it's not true. You need to take whatever the sign is of your delta H, plug that in for delta H, and then make sure you have this entire quantity negative. So moles of silver chloride canceled. This moles times delta H would tell you the total heat that's being released from the system into the surroundings. So now we have to deal with our surroundings. So in this problem, we have been given the mass of the solution at the end. It's 101.8 grams. We've been told the specific heat of the solution, it's basically that of water, 4.18 joules per gram times degrees Celsius. Does anyone notice a discrepancy in the units of energy here? So kilojoules and joules. So you have to decide, one side needs to get converted. I'm gonna just do it here. I can say there's 1,000 joules for every 1 kilojoule to get this in kilojoules per gram times degrees Celsius. And then they're wanting the final temperature. I don't know that. That's what I'm solving for. That's TF. And I do know the initial temperature, 22.60 degrees Celsius. I'm running out of room. So this lecture has gone on so long. I'm not going to finish this, but I'll just tell you the final temperature is 23.32 degrees Celsius. And you should convince yourself of that by solving for TF.